Hi everyone! When I got started learning Yolo v3, I noticed that it's really difficult to understand both the concept and implementation. Even though there are tons of blog posts and GitHub repositories about it, most of them are presented in complex architectures. I'm not going to cover how Yolo works in theory step by step. I'll try to cover more in detail all parts from the past tutorial and parts I missed last time. If you're interested, you can check my past tutorials in the description below. And in these tutorials, I tried to explain a whole theory in it. I thought I implemented it in TensorFlow 1.15. But more and more people write me about errors because they try my code within TensorFlow 2. So I decided that it's time to write Yolo v3 implementation to TensorFlow 2.1, and maybe I'll make more tutorials with it. So based on this experience, I'll try to write code in this tutorial to make it easy and reusable for many beginners who just got started learning object detection. Without overcomplicating things, with this tutorial you'll be able to simply implement Yolo v3 in TensorFlow 2.1, at least for now. In this tutorial series, I will give you solutions on how to train Yolo model for your own custom dataset locally or even on Google Colab, because I received a lot of requests. So what are the prerequisites for this tutorial series? So you should be familiar with Python 3, understand object detection and convolutional neural networks, and basic TensorFlow usage. Of course, I will begin with introduction with Yolo the algorithm, which started in 2015 by Redmond G. et al. Proposed the Yolo network, which is characterized by combining the candidate box generation and classification regression into a single step. When predicting, the feature map is divided into 7 by 7 cells, and each cell is predicted, which greatly reduces the calculation complexity. Also accelerate the speed of target detection by frame rate of up to 45 frames per second. After a lapse of 1 year, Redmond G once again proposed Yolo v2. Compared with the previous generation, the mean average precision of the WOTS VOC 2007 test set increased by 20%. However, because a cell is only responsible for predicting a single object, facing the goal of overlap, the recognition was not good enough. Finally, in April 2018, the author released the third version of Yolo v3, which we are talking in this tutorial series. Compared with RetinaNet, RetinaNet has an input size of 500. In the case of 500 by 500, the detection speed is about 100 milliseconds. That's quite slow. And while Yolo 3 has a detection speed of 29 milliseconds per frame when the input size is by 460 by 460. This slide is enough to prove that Yolo v3 has achieved a very high accuracy and speed rate. The author treats the object detection problem as a regression problem in Yolo algorithm and divides the image into S by S grid image. If the center of target falls into a grid, the grid is responsible for detecting the target. Each grid will output bounding box, confidence, and class probability map among them. The bounding box contains 4 values, x, y, w, h. And xy represents the center of the box and wh represents the width and height of the box. Confidence indicates the probability of containing objects in the prediction box, which is actually the I/O value between the prediction box and the real box. The class probability indicates the class probability of the object, and the Yolo v3 uses the two-class method. For those of you who don't have a lot of experience with Yolo v3 or other object detections, I recommend to read my past tutorials or watch my YouTube videos and try to understand how the algorithm actually works. As its name suggests, you only look once, applies a single forward pass neural network to the whole image and predicts the bounding boxes and their class probabilities as well. This technique makes Yolo quite fast without losing a lot of accuracy. As mentioned in the original paper, Yolo v3 has 53 convolutional layers called darknet 53, which is shown in the following slide, which is mainly composed of convolutional and residual net structures. It should be noted that the last three layers, average, pool, connected, and softmax layers, are used for classification training on the ImageNet dataset. When we use darknet 53 layer to extract features from the picture, these three layers are not used. So on the left side you can see the whole architecture, which is described on the paper, and on the right side of the slide you can see darknet, how I implemented it in the code. And of course you will be able to download it from my GitHub repository. It's open source. From previous darknet 53 architecture slide, it's quite impossible to understand or imagine how Yolo v3 works. So here is another figure which Yolo v3 architecture. From this image you can see that Yolo makes detection in 3 different scales in order to accommodate different object sizes by using strides of 32, 16 and 8. This means if we'll feed an input image of size 416 by 416, Yolo will make detections on the scale of 30, 26 and 52. The first detection scale yields a 3D tensor of size 30 by 30 by 255 actually. After that, Yolo v3 takes the feature map from layer 7 to 9 and applies one convolutional layer before upsampling it by factor of 2 to have a size of 26 by 26. This upsampled feature map is then concatenated with the feature map from layer 61. Actually, the concatenated feature map is then subjected to a few more convolutional layers until the second detection scale is performed at layer 94. The second prediction scale produces a 3D tensor of size by 26 by 26 by 255. The same design is again performed one more time to predict the third scale. The feature map from layer 9 to 1 is added one convolutional layer and is then concatenated with a feature map from layer 36. The final prediction layer is done at layer 106. In summary, Yolo predicts over 3 different scale detections, so we feed an image of size 460, 460, and it produces 3 different output shape tensors. But still, seeing darknet 53 and Yolo v3 structure, we can't fully understand everything. This is why I have one more slide with the overall architecture of the Yolo v3 network. Here it is. Now we can see that the input picture of size 460 gets 3 branches after entering the darknet 53 network. So here's our input image and here's our darknet network. These branches undergo a series of convolutions, upsampling, merging and other operations. 3 feature maps with different sizes are finally obtained, with shapes of 30 by 30 by 255, then 26 by 26 by 255, and of course 52 by 52 by 255. And this image is not mine, I didn't draw it, but this picture explains the best how Yolo architecture looks actually. The most significant feature of the residual model is the use of shortcut mechanism, somewhat similar to the shortcut mechanism in the circuit, to alleviate the gradient disappearance problem caused by increasing the depth in the neural network, thereby making the neural network easier to optimize. It uses an identity mapping to establish a direct correlation channel between input and output so that the network can concatenate on learning the residual between an input and output. So you can see this is a simple residual module, and here is the code how it's implemented in my code. Often you don't know how it looks in code if you know how it looks visually, and and vice versa. So here it's a slide which shows everything for you. Next, to know the prediction process of Yolo in detail, it's necessary to first understand what are the feature maps and embeddings. So feature map, when we talk about convolutional neural networks, we always hear the word feature map. It's also called feature mapping. Simply put, the input image is convolved with the convolutional kernel to obtain image features. Generally speaking, when convolutional network extracts features from the bottom up to the image, the number of feature maps will increase and the spatial information will decrease. And its feature rules also became more and more abstract. For example, the famous VGD16 network, its feature and map change showed in this image. The feature map is getting smaller and smaller in space size, but getting deeper and deeper in the channel size. Next, feature vector. When it comes to the feature maps, we can often hear it mentioned in the field of face recognition. Generally speaking, it's actually a feature map that is extracted by the last fully connected layer into a feature vector. As early as 2006, Hinton, the originator of deep learning, published a paper in Science. For the first time, a self-encoding network was used to extract a feature vectors from MNIST handwritten digits. It's worth mentioning that this paper also opened the road to the rise of deep learning. When convolutional networks extract features from the bottom-up image, the resulting feature map is generally getting smaller and smaller in space size and getting deeper and deeper in channel size. This is related to the mapping of region of interest to feature map. In following slide, after a region of interest in the original image is mapped into convolutional neural network space, the space size on the feature map will become smaller or even point, but the channel information of this point will be very rich. The information, the feature representation of the image information is the region of interest area mapped on the convolutional neural networks. Since the pixels in the image are closely connected in space, this results in great redundancy in space. Therefore, we often eliminate the redundancy by reducing the dimension in space and increasing the dimension in the channel, and try to obtain its most essential features in the smallest dimension. So here's an image, and for example, the red region of interest in the upper left corner of the original image is mapped by the convolutional neural networks, and only one point is obtained on the feature map space, but this point has 85 channels. So the dimension of region of interest has changed from the original 32 by 3 to the current 85 dimension channel. This is actually an 85-dimensional feature vector obtained after the convolutional neural network performs feature extraction on the ROI. The first 4 dimensions of this feature vector represent the candidate box information. The middle dimension represents the probability of judging the presence or absence of objects, and the following 8 dimensions represents the classification probability information for 80 categories, talking about COCO dataset. Well, next I'll talk about Yolo v3 multiscale detection. Yolo performs coarse, medium, and fine meshing of the input image to enable the prediction of large, medium, and small objects, respectively. If the size of the input picture is of size 460 by 460, the coarse, medium, and fine grid sizes are 30 by 30, 26 by 26, and 52 by 52 respectively. In this way, it's scaled by 32, 16, and 8 times in the length and width respectively. The output of the 3 branches of the Yolo v3 network will be sent to decode function in my code to decode the channel information of the feature map. In the following picture, the black dotted box represents the Anchor and the blue box represents the prediction box. The dimensions of the bounding box are predicted by applying a log space transformation to the output and then multiplying with the Anchor. Here in this slide, B denotes the length and width of the prediction frames respectively, and P denotes the length and width of the hardcore frame respectively. T represents the offset of the center of the object from the upper left corner of the grid, and C represents the coordinates of the upper left corner of the grid. Next, non-maximal suppression, as the name implies, suppress elements that are non-maximal. Non-maximal suppression removes those bounding boxes that have a higher overlap rate and a lower score. The algorithm of non-maximal suppression is straightforward, and iterative process is as follows. First, determine whether the number of bounding boxes is greater than 0. If not, then end the iteration. Second, select the bounding box A with the highest score according to the score order and remove it. And third step is calculate the IOU of this bounding box A and all remaining bounding boxes and remove those bounding boxes whose IO value is higher than the threshold. Repeat the above steps. As you can see in the Yolo algorithm, there are two cases of non-maximum suppression processing. One is that all prediction frames are processed together with NMS, and the other is that NMS processing is performed separately for each category of prediction frames. In the later case, there will be the phenomenon that the prediction box belongs to two categories, which is more suitable for the case where multiple objects exist in a small cell at the same time. Up to this moment, we covered all the three we did for simple use of Yolo v3. In the next tutorial part, I will cover other functions needed for custom object detection training. Now we can try implement a simple detection example. I'll talk now about implementation. This is only the first tutorial. Not to make it too difficult, I'll do a simple Yolo v3 object detection. To make it work with TensorFlow 2.1, we need to do three following steps. So first, construct and compile Yolo v3 model in TensorFlow and Keras. Transfer weights from original darknet weights to constructed model. And third, test object detection with image or video, it doesn't matter. I will not show full code in this video tutorial. If you're interested, you can download my code from GitHub, which link is on my video description. So first, here are the steps, but you can check these steps on my text version tutorial or you can find these on GitHub, it doesn't matter. So first, here is my project folder. I already have it, and first step you will need to do is you'll need to clone a GitHub repository from, of course, link I'll give you to you. It will be posted in this tutorial. Next, you will need to install the requirements. Well, maybe I'll add more later, but for now I don't know what to add more. Mostly you need TensorFlow and OpenCV and of course NumPy. And now we need to download train Yolo v3 weights to model data, and of course you'll use a widget, or you can download it manually if you're on Windows. So to model, here it is, Yolo v3, and I have a Coco names here. You'll need to have the same stuff. And here is my Python detection demo script. I can open it, and of course it's very short and it's quite easy. And here I have an image, so images treat JPG. Here it is, a few example images, and I'm not going to run this from Python idle. I will open a terminal, and now I'll write a Python detect detection demo, just like that. Let's try it. Running. Oh, sorry. Because I'm using OpenCV, it will not show me while I run this from terminal. So we can simply run it from here because it will open it for us. I'll close this one. So as you can see, this is our simple example and it works. And of course I can change the image, so I'll use a kite. It's on CPU, so it takes a little while for me. So as you can see, it works. Let's try a video. Probably you can do this also. And this is on CPU. Let's run this on GPU probably. It takes a while to start. Oh, sorry, I don't have this image. Give me a moment. I'll find where I have it. I don't have a video. So here it is. And right now I have a video right here, and let's run and see how it works with a video. CD drive MP4. Oh, it's street drive. Sorry again. Street drive. Let's run. So as you can see, it's working, and actually it's the main Yolo v3 algorithm. And as you can see, here it writes frames, how long it takes to process one frame to detect and show it for us. And actually it's working. If you would ask where I received this video, I actually found this on YouTube. I downloaded it, cropped 2 minutes, and here it is. I have a testing video with a lot of objects I can detect. So that's it for this tutorial. In the next part I will cover more theory related to custom Yolo v3 training, and of course we'll train our first custom object detector. So see you there, my friends. Goodbye. That's it.